Hi, we're here today with
Dominic
and me, and today we're talking about automatic symmetry discovery with Lie Algebras, CNNs. If you want to join the reading group sessions yourself, you'll find all the information in the description.
Yeah, so this is, first of all, thanks for having me here. This was joint work with Robin Walters and Yan Chen Liu, Dashun Wang, and Rose Yu. Rose Yu has been my longtime collaborator on many of my machine learning papers. Here, basically, the idea that we wanted to follow was try to see if we can simplify what people have been doing by trying to encode symmetries into neural networks. And the thing is, in machine learning, oftentimes the way people think of like why symmetries are useful is because you might have, for example, in images you might have a pattern that is transformed in some way using some symmetry group. Maybe it's shifted or rotated or something. You still want to be able to match those patterns without having to relearn like new patterns, basically new feature maps for every shifted version. So based on that idea, people think that using symmetries is gonna basically help with generalization and reduce the amount of parameters that you need. But in physics, there is a little bit more to symmetry. So a lot of, and this is actually a slide from Michael Bronstein's keynote where he was saying basically physics and symmetry are the same, quoting Paul Anderson. Basically in physics, a particular way of talking about symmetries, especially it's called like gauge symmetries. There are some papers on gauge symmetries in machine learning too, but I think they're still fairly far away from what gauge theory is in physics. But essentially all of the fundamental forces in nature can be expressed as some changes in local frames of a symmetry group, basically. So I can tell you more details if you're interested in it, but essentially physicists are more interested in symmetries than just pattern matching. It's a lot more about like actually defining forces and how nature works. So I'm going to skip through some of these slides and just go directly to what we're talking about in the paper. I think one of the earlier papers, the recent wave of symmetry equivariant neural networks, group equivariant neural networks, started with maybe this paper and maybe one older paper by the same people, by Tucker Cohen and Max Welling, where they tried to generalize convolutional neural nets by encoding a different symmetry group into the neural network. In this case, they were encoding like fourfold rotations into the neural network. And a lot of work happened since then, and people showed that, for instance, if you encode the symmetry structures of, let's say, Hamilton's equations of motion, which are describing like Newtonian physics, you can get much better prediction of trajectories in the long run. And a lot of papers similar to that came out. And basically all the premise is that usually when you encode symmetries, you're reducing the number of learnable parameters, and it may help with generalization of the model. And what was the thing that we wanted to tackle about this? We saw that most of the papers who are trying to encode symmetries, if they're dealing with a continuous group, they usually go two routes. One is they either discretize the continuous group. For example, you might have, let's say, continuous group of rotations in 2 dimensions, and then you choose just certain angles and pick those as the elements of the group that you want to represent and encode into the model. Or they do something that's a little bit more sophisticated, which is like they use what is called the irreducible representations of the group, and then do a sum over a few of them. You generally need a lot of them to have an accurate description of the group, but they basically do some truncated sum over the irreducible representations to do this. So one issue with these methods, and I will focus mostly on the first one, is if you are dealing with a high dimensional symmetry group, for example, let's say the simplest case for 2D rotation, you have SO2 is basically a circle described by like just the angle of rotation. So in order to capture this group well, you have to pick a number of points on the circle to describe basically which rotations you're encoding into your neural network. If you have, let's say, then 3D rotations, then you have a 2D surface. And if you have 4D, then you have a 3D hypersphere that you're dealing with. So the points that you need to sample from are basically the group manifold, which is actually a little bit more complicated than just these spheres that I described. As you have the same issue as you would encounter in many problems dealing with dimensionality, that as the dimensions go up, you need to sample, basically the number of samples that you need to take kind of grows exponentially with the number of dimensions.
But it's not so severe, right? Because usually we're just dealing with, or if I'm doing my 3D space stuff and want to look at symmetries in 3D, then well, we just have 3 dimensions.
So if you know, yes, so if you do know the symmetry groups that you are dealing with, and you know that they are low dimensional, you can say that, okay, maybe it's not that severe. But even in 3D, with like sampling points on a sphere, it's, basically exponentially more relative to just sampling rotations on one circle. So the number of things that you need to encode into your model grow very rapidly if you wanted to go to higher dimension. And now I'm thinking, for example, if you are dealing with groups that are not compact, like the Lorentz group, for example. So for special relativity in physics, you're dealing with the Lorentz group, which is basically hyperbolic along the dimensions that involve time, meaning that you basically you have like an infinite space of number of points that you need to sample from.
Oh, is this like we have 3 dimensions of space and 1 dimension of time? And
yes, exactly. And the time dimension, so when you're thinking of rotations, you have like a circle to deal with. But if you were thinking of Lorentz boosts, so things that involve like time and 1 spatial dimension, instead of a circle, you have a hyperbola. And it's basically going into infinity. So it's a non-compact group. And there, you have to make a choice. How do you sample from this non-compact dimension? So essentially what we wanted to say was that there must be a way to deal with symmetries and encoding symmetries into your neural net without having to sample from the whole space. And I think I had some analogy there that might help compare this with some other ways that we do neural net. I think you can kind of compare this stopping to sample the whole group and trying to find some generators that create all of these different group elements. You can compare that with how essentially convolutional neural nets deal with this picture, right? So the fully connected network would have a filter for each of these cat pictures for each of these locations. But what the convolutional neural net does is it has one pattern for the cat, and then with the convolution operation, it takes you, it matches the pattern anywhere in the picture. It's not exactly the same as what I'm going to talk about, but basically our idea was, can you, instead of discretizing the group, can you have a construction that generates a sufficiently large set of group elements from very small number of parameters without you having to encode the group elements directly into the network? So that is the idea behind what we try to do. So I'm going to skip some of these, and essentially we wanted to tackle problems that you might get with, like, when you're using discretization or these other methods. And like, so for when you discretize a group, you have this error of like, because basically you need a lot of samples from the group in order to reduce your error from discretization. With the second method that I didn't describe much, you need to actually know these functions that are the irreducible representations of the group, which also means that you need to know exactly what group you're dealing with. And for every group, those functions, those irreducible representations are different, and you need to encode them as functions into your neural network separately. So basically for every new group, you need a whole new set of samples and architecture, basically re-implementing your architecture.
And
so we wanted,
then also we still have this approximation error, right? Because people usually only use very few, like for example, if we have the spherical harmonics now, we only use very few coefficients.
Exactly. Yes, that's exactly one example of that. That the spherical harmonics are the irreducible representations of SO3.
Yeah, that's the only I know.
Right. No, yeah, that's a very good example. That's exactly what is happening there. And then depending on what you're dealing with, you need to choose basically a set of these irreducible representations. So for spherical harmonics, really what they are is like the same way that the Fourier series represents different frequencies in function space, like in one dimension. Spherical harmonics are doing that in spherically symmetric things, basically things that don't change over the radius. And if you want to have higher frequency, like functions that are sharper or like oscillating faster, you just need more and more higher order of the spherical harmonics, basically higher L and M of the YLMs to capture those. So we wanted to find a way. We basically said there must be an easier way to do this that, you know, doesn't involve knowing these complicated functions and having to encode those, because I really usually don't like memorizing any such complicated functions. I think there must be a simple way to do this. So that's what one of the main motivations. The other one was I was also kind of inspired by what we do in physics. For instance, like a lot of times, I mean, we talked about Lorentz symmetries, for instance, like it took people a long time to discover Lorentz symmetries, but eventually did, you know, by looking at the data and so on. So with Einstein's special relativity, I want, if we restrict ourselves to groups that we predefine and encode into the neural net, then we cannot discover anything that's not a subgroup of what we have already encoded. For example, if we were only dealing with compact groups, and let's say we encoded SO4 or something like that into a neural network model, it would never be able to match Lorentz symmetries, because that's a totally different group that is not a subgroup of SO4. And if you wanted to encode a group that would encompass all of the groups, that's a massive group. It's the general linear group that you need to encode. And there, I think, basically sampling that group is essentially hopeless. So we were basically also asking the question, can you have a method that's simple enough that so that it's also able to discover symmetries from data. So our goal was not to come up with a very sophisticated, complicated model. It was rather trying to go through the math and see what is the simplest thing that simplest building block that could, first of all, create the other group equivariant neural networks that people have constructed. And secondly, could it be simple enough that it would allow us to learn symmetries potentially? So, and that is basically what we think we came up with. And just as a spoiler here, I mean, not a spoiler, but just a teaser for what's going to come. In the end, the architecture turned out to be very simple. You can really understand it as a group, as a graph neural network, where instead of the graph structure, you have these Lie algebra elements. So what is the Lie algebra? I will explain that in a second. But basically, those are like small transformations that you can combine to create larger group elements and larger finite group transformations in a continuous group. And while we did this, also at the end of it, I don't know how many of you are physicists or are interested in physics, but something that I was very excited about came out of this is that basically we found some relations with some symmetry encoding physics models that people have worked with for like 100 years. So I hope that it could have some use in physics. Okay, so since we're gonna go over the paper soon, I'm just gonna quickly go through these parts, and then if you have more questions about the details of the math, we can also talk about it while I'm going through the paper. But essentially what we're dealing with here is a continuous group, which is basically the group is a set closed under a set of operations, and it has an identity element and an inverse for every element. And when we say a continuous group, it usually has what is called a group manifold. So it's like a differentiable space that represents the group itself. And the Lie algebra is really the tangent space around the identity element of the group. The identity element is that basically like the matrix, identity matrix, that, if you multiply it into anything, it doesn't give you anything else. And
yeah. Like, what does our, like, a continuous group, discrete group? Then I can think of the discrete group being the group of like 4 rotations, for example, and the continuous group being all rotations along, not just in the 2D plane now. And what do we additionally need to make it a manifold?
Oh, so for the continuous rotations, for example, the manifold is really the circle that is represented by starting from one point and then going through all the angles. So a manifold is a space that locally looks like Rn, but you have a transition function that tells you how the Rn that you can describe, basically how the mapping from one neighborhood to Rn and the mapping from a neighboring neighborhood to Rn kind of transition to each other in the places where these two neighborhoods are overlapping.
Okay, and now in your drawing, the G, the big G, is we can see as the ball right here. Let's say we're just looking at the group of rotations in 3D, and the G is this manifold, and then you look at now spaces that are tangent at one point to this manifold.
Yes, exactly. And so, for example, if you think of this as like, the sphere parameterized with theta and phi, like the azimuthal angle and the polar angle, this tangent space, the basis vectors that you can define in this tangent space are also like, d theta and d phi, those moving along those two angular directions. Actually, it's a little bit more complicated because there's like sine of theta is multiplied into the magnitude of like when you do the spherical coordinates. So those come into like how these basis vectors are defined. These L's that we're talking about are not just the vectors themselves, they are actually transformations that you can use them basically as matrices, and then you act on one point with them, and they take you to that point plus, for example, d theta or plus d phi.
Okay, so what's the C right here?
Oh, so these C's are called structure constants of the Lie algebra. And they basically define the structure of the Lie algebra, which is mapped to the structure of the
They
group.
tell us how much we go into each L direction, right?
Yeah, so this is saying if basically the reason this is called an algebra is that, or Lie algebra is that under this commutation relation, if you think of these as matrices, for example, in 3 dimensions, then when you do the commutators of these two matrices, so Li, Lj minus Lj, Li, then you get another one of these matrices, Lk. So under this commutation operation, these matrices are closed. And when they are closed under a bracket like this, they're said to form a Lie algebra. And the coefficients that define how these things are related to each other are called the structure constants of the Lie algebra. And they differ from one group to another. So for example, for rotation groups, these are, do you know the epsilon ijk? Have you heard of those? There's like this set of, you can build basically a tensor with 3 indices that is anti-symmetric under the permutation of every 2 adjacent indices. I feel actually maybe it's better if I also use my, I'm trying to see if I can use my other laptop to write some stuff, but maybe it's easy to just do that here.
If you go to the,
Yeah, so for the rotation group in 3 dimensions, these CIJKs are actually identified with what is called the epsilon IJKs. These are called the Levi-Civita pseudotensors. So essentially, this has the property that epsilon 1, 2, 3 is 1. And then if you permute any 2 indices that are next to each other, you get a -1.
okay.
So epsilon 2, 1, 3 is -1.
But then that immediately brings up the question of why this is an interesting matrix, so to say.
So yeah, so these, if you write out, so maybe, yeah, maybe I can show a little more about Lie algebras. Actually, let me just try to show that here with.
Like I think probably the most important part about Lie algebras is why we can now get to all of the group elements or represent all of the group elements with just these bases.
Yes. So I think, so let me see if I can, just opening the, what is this? Oh, yeah, got it. So I'm just going to quickly show you, I think, from the Wikipedia page, just a couple of examples here. And let me zoom in here. Let me see if they have the example for just 2D rotations.
2 dimensions.
This could also work. This is one example of, let's say, where these are, let's say, if you take these matrices X and Y, if you build basically higher powers of x. If you take x to any power, it just gives you x again. But if you take y to higher powers, then it can alternate, I think, between the one is going to move to different places, essentially. So you can multiply this into, well, let me see. Is this?
I think it would just be 0, right?
Oh, this is nilpotent actually, right? If it's 1, 1, yeah, that's right. This is only going to give you 0. So maybe this is not a good example. Let me see if SON, but I can also just quickly show something here about, for example, the rotation group. So suppose we're talking about those 2D rotations. So the rotation matrix that takes, 1 point in the angular direction by an angle theta, the rotation matrix looks something like this. It's sine theta, yeah, cosine theta, sine theta, minus sine theta, cosine theta, and you can switch the minus sign up and down depending on your convention. But basically, if this acts on any point that is given by x and y, it takes you to some x prime and y prime where these points have been rotated by an angle theta. Now, the idea of Lie algebra is you look at infinitesimal transformations and say, what do infinitesimal transformations look like? And they should be identity transformations plus a small transformation that's not identity. So if you want to get infinitesimal transformations, you want to write out when basically theta goes to some small epsilon, what do these look like? So cosine is going to look like 1 minus, epsilon squared. Basically, you can say epsilon squared over 2. So there's an epsilon squared term. So order epsilon squared terms are going to follow. But for sine, you're going to have epsilon itself as the first order, and then you have order epsilon cubed. Now, if epsilon is infinitesimal, then you can neglect all these higher order terms. So what you end up with is G is approximately 1 epsilon minus epsilon 1.
Okay, maybe just real quick, for the cosine, we're looking at the Taylor expansion of the cosine, and that's just that's why we have the 1 and then the order of epsilon squared stuff there, and the same for the sine.
Exactly. Yes. Yes. Thanks for explaining. This is I'm doing the Taylor expansion, and then you just get basically something that is we're only keeping up to first order in epsilon.
Yeah.
So then what you can write this as is 1 plus epsilon times this matrix, 1 minus 1, 0, 0. This is what we're calling the Lie algebra element for constructing the group of rotations in 2 dimensions. So basically, SO2, which is the name of this group, it means special orthogonal group in 2 dimensions. Orthogonal means their matrices satisfy G transpose G equals identity. This and special just means that their determinant is equal to 1. So that of G is equal to 1. So this group actually is the group of rotations in 2 dimensions. And if you look at infinitesimal group elements, they can be written as identity plus an epsilon times this matrix that I'm calling L. Now, the interesting thing is you can construct all of the larger group transformations using this matrix L and using what we call an exponential map.
And here, in this case, you only have one L to construct the whole group, right?
Exactly, yes.
Yeah, I just, sorry to interrupt. I don't know if this helps, but I think the question came up is what is the relationship between the Lie algebra and the Lie group? And
Yeah.
yeah, there's this Lie's third theorem sort of explains that correspondence because the Lie group is a manifold. And so you're basically mapping from into, from one manifold to a second, but I think it's somewhat complicated. I mean, that relationship is not, I mean, I agree, it is an exponential map, but why there is this correspondence between the Lie algebra and the Lie group is, somewhat,
Yeah. So for more complicated groups, it's actually harder to show that every Lie algebra can basically corresponds to a Lie group as well.
Yeah, I think we can be happy with the 2D group now, and I just continue this explanation. I think that's
okay.
Fine.
Yes, so I will. So in this simple case, the exponential map, you can really understand it as writing out the Taylor expansion of the exponential and then doing that for matrices. So for example, basically, if I call g of theta, basically the rotation by an angle theta, you can write that as exp of theta times L. And the way this is defined is you write the Taylor series for the exponential. So k is equal to 0 to infinity. And you just do theta to the power k, the matrix L to the power k, divided by k factorial. So in this case, it's really literally just an exponential function, and you can write it out. In more complicated groups, and when you don't have so groups do not necessarily, continuous groups do not necessarily need to be in the matrix form. This is, so whenever you have a matrix for your group elements, it's called a group representation. Basically tells you that it is acting on a particular space in a particular way, in a vector space in a particular way. Then when you have a group representation, you can use the matrix exponential to define the exponential map. But there are some details there. It's not always, the simple exponential is not necessarily going to cover all of your group elements. In cases where you don't have a group representation, you can still talk about the group, the exponential map as the exponential map as a map from the Lie algebra to the Lie group in a formal way. It doesn't have to be exactly just a matrix exponential.
So the exponential map is just what you call the operation that takes us from the Lie algebra element. What do you call those? The Lie algebra elements. So in this case, the L.
Yes.
What do you call the L again?
Yeah, so L is a Lie algebra element. It's also a basis for the Lie algebra.
Okay.
So if you have a set of L's that are closed under commutation relations, they form a basis for the Lie algebra. So for example, in that slide, I had Li and Lj were equal to Cijk, Lk. If you find a set of Li, basically a set of Li's with some indices I, is a set of elements in your Lie algebra who form, basically satisfy this relation, meaning that if you take their commutators, you end up with another one of those elements that you chose, then it's forming a basis for your Lie algebra. So this L is an element as well as a basis for your Lie algebra.
Okay, cool. And now we also have in the chat the question, like where did the identity, so to say, go, our starting point? Now that you wrote down the g theta as exponential of theta L, where did our starting point go?
Yeah, so when we have k equals 0, k factorial is 1, theta to the 0 is 1, and L to the 0 is also identity.
Okay.
This is one thing that we need to define for matrix powers actually. Yeah, so we're assuming here that it's, yeah.
Okay, perfect. I think this was a pretty nice explanation.
And just one last thing about for the LIJKs, I'm just going to give you a teaser for like a group of rotations in 3 dimensions, which is the special orthogonal group in 3D, which is 3 by 3 matrices satisfying G transpose G equals identity and determinant of G is equal to 1. 1. These matrices, you can build basically 3 generators, which are very similar to the 2D generator, but they have 1 extra dimension. So for example, and when I say generators, this is like a bad habit from physics. This is an infinitesimal generator of the group is a Lie algebra element. So I sometimes, instead of saying Lie algebra basis or Lie algebra element, I'll just say generator. If formally a generator of a group can be any group element that can be used to generate all the other group elements, but L is not a group element. It's actually identity plus epsilon L that becomes a group element. But so I sometimes misuse this nomenclature and just say L. So here you see for 2D, you had 0, 1, minus 1, 0 was a generator, was a Lie algebra element for 2D rotations. For 3D, you can have a rotation about the z-axis by this matrix, which is exactly the old matrix that we had, but now you have this extra dimension that's 0. And then you can have a rotation around the x-axis in a similar way. I think you need to just flip the minus sign and put it around the other axes. So you see on the x dimension, you have only zeros, but in the other block, you have the same generator that you had for rotations in 2D. And for y, you can have a similar situation, except that the middle block has to be zeros. So, sorry. These have to be zeros, and then this is 1 and minus 1. I think these are the correct generators for the 3D rotation. And what you can do is you can compute what Lx times Ly is, and then minus Ly times Lx, and you should find that it becomes equal to Lz. So this here, this coefficient 1 here is the Cijk. So technically it is, C of x, y, z is 1, if I'm labeling them by x, y, and z. And this right here is the commutator between Lx and Ly. So this is a simple practice that you can do for yourself to familiarize yourself with the algebra. Again, this is for representation of the group, meaning that the representation of the Lie algebra in this case, which is that the Lie algebra, basically the Lie algebra elements are represented as matrices. In general, they can be abstract objects. But okay, so maybe
then how do we use this? What do you do with it?
Yes, so let's go back to maybe it's better if I just open the slides on this computer so that oh, doesn't matter. Okay, if I need to say something, I'll just go back to that.
Okay.
Okay, so what do we do with this? We basically, this is what you just saw was a glimpse of how you can, like the exponential that I wrote out was a simple example of a case where you could use the Lie algebra to construct any Lie group elements. So this is basically the gist of our idea. To say, instead of having to sample a lot of group elements, which might be complicated in their form of matrices or like, whatever representations you want to use, instead of doing the sampling over the group, maybe it is easier to have the Lie algebra elements as the only things that you encode. So instead of encoding the G into your group, into your architecture, you just encode the Lie algebra elements, and the parameters, the number of these parameters that you choose here, these parameters will be the only things which are basically a vector of numbers, the coefficients that you're giving to each of these Lie algebra elements. These parameters could generate all of the group elements that you need, all of the samples from the group that you need.
So instead of having, like, let's now again just imagine 2D rotations, instead of having, say, one parameter or one set of parameters for all 90-degree rotations, I could also have like one set of parameters for like the Lie algebra element or the generator, and then have 4 additional parameters telling us how much the rotation.
So maybe slightly differently. So what I mean is, if you are doing the encoding of 2D rotations, you have to encode that 2x2 matrix, the cosine theta, sine theta, and so on. Okay, sorry, I can't write well here.
I think we all have it in mind. Yeah.
So cosine and sine. So you have to encode each of the group elements is this 4x4 is by 2x2 matrix, and you're encoding a lot of these 2x2 matrices into your architecture. What our approach is, the difference is that you encode just one 2x2 matrix, which is the L, and instead of all the other ones, you just have one number for each one of them, which is the angle theta.
Okay.
So the angle is what generates the other elements, and the only 2x2 matrix that you have is L.
Yeah, that sounds good to me.
And yeah, and then right now, so this way it sounds like, okay, it's not that different. We're just changing it from, like, instead of encoding the whole matrices, you're just encoding these angles. But it's a little bit more than that. It's so basically now I'm going to jump to what the main theorem of the paper is trying to say. Oops, maybe I should have cleared this. And that is basically saying the following. So I'm not gonna, and we can discuss about these push forward and these vector fields also if you want, but this is some detail that we can talk about later. But the main thing that we discuss in the paper is, so when you're doing these, looking at each of these group elements, they do a corresponding transformation on the space. So here S is the space on which the group is acting, for example, the points that are going to be rotated. And if you pick some point of origin, x0, when you do the group transformations, they take you to some other points in the space. So there's basically the structure of the group is somehow mapped also on this space, which is not a very important issue right now. But when we want to talk about what this focusing on Lie algebra elements does compared to what other people have been doing, I need to just tell you briefly what it means to be basically a group equivariant architecture, and what it means to be encoding a symmetry into the group. And this is basically the start of everything. So the main thing is, we're assuming that there is, we have a space where the points on the space are called X. Let's say this could be pixels in the location of pixels in an image. Then we have a feature map. Let's say the image itself is some function defined on these coordinates. It's saying this point is bright, this point is red, and so on. So that's f of x is, for example, the image itself. Okay, and when we're acting with a group element on an image, what we do is we're basically changing, for example, if we're rotating an image, what we're doing is we're reassigning the coordinates of which pixel should be bright and which pixel should be dark. And you can write it as basically the inverse transformation acting on the coordinates of the pixels inside the image. Then what is what is an equivariant map? What is a group equivariant map? Basically, group equivariance means that we want to do a transformation on these feature maps, these little f's. So I'm going to call the transformed versions, the transformation that we're doing on the feature map, capital F. And this capital F is called an equivariant map if basically a transformation done on the output of this map becomes a transformation done on the input of the map. So it's like if I, for example, I don't know, do a grayscale of a color image, this is an equivariant map. Why? Because if I rotate the color image and then do a grayscale of it, it's the same as doing the grayscale of the image and then rotating the image. So it's the transformation can basically pass through this layer that is doing the grayscaling of the image. So the main result that we're building all our work on is this result by Condor and Trivedi, and there was a similar result by Cohen and others, which basically said if you have a linear layer, so a linear map, if this F is linear, and it is equivariant under a given group, then this layer must be doing what is called a group convolution. So this is generalizing the regular convolution operation to a group element. So in the regular convolution, you would have, for example, G minus V. In this in the group convolution, you have G minus 1 times V, acting on V. And here, kappa is the convolutional kernel, which is basically a distribution over the group manifold itself. So this is a, oops.
I think he got disconnected.
Presenting the points in space with their equivalents in on the group manifold. This is called lifting the group elements to, lifting the points in space to the group elements.
Sorry, Nima.
Sorry, any question? Yeah.
Yeah, I didn't realize I was muted. But yeah, you were cut off when you started explaining the or when the notice popped up on your screen.
Yeah.
Oh, really? Sorry. Oh, which part did you not hear actually?
Since the pop-up.
Yeah, I would say we now have this convolution, and we know that every or we know that something is only equivariant, or a function is only equivariant if it can be implemented as a convolution. And we now have this knowledge of why is it important for us now.
Yes, so now basically this was the theorem that people use to build layers that can have this property of passing a group action through. And why is this important? It's because basically you sometimes want to have your layers to be such that they preserve the properties of symmetry properties of your input.
Sure.
So what we did, basically what people were doing was trying to implement this group convolution in by sampling over the group to do this integral. So they want to do this integral. In order to do this integral over the group, they need to have a lot of different group elements. So they know basically they replace this integral by a discrete sum over group elements. And what we wanted to do is say, okay, if you, instead of using the full group, use the Lie algebra of the group, then what will you find? And will that help you simplify this, doing this integral? Can you avoid having to sample over the whole group?
Okay.
I have a question here about this group convolution. So when you say you want a group convolution for a group J, does that mean that you want, for example, if your group is a rotation, you want a convolution that instead of preserving translation invariance, the one we usually know. You want a convolution that preserves the rotation invariant. So kind of instead of a translating window, you have this rotating window, right? Is that what you mean? Yeah.
Yes, exactly. So that's basically what the group convolution is doing. Yes.
Okay. And what you mean, like with the other papers, when they sample, for example, 4 rotations, it's kind of they discretize this integral in terms of like the sum of 4 different elements.
Exactly.
Okay.
Yes, exactly. So the discretization happens at this space, at this step, when they want to do this sum over the group elements. And then we said, okay, what happens if somehow your model is focused more near identity rather than basically having to sum over all the groups? And the idea is the following. This kernel that, and I just rewrote the convolution just in a slightly different way. G, here it was like G minus 1V, but you can do a change of variables and just write it as VGV. So we have this convolution operation, and then we ask the following question. What if your kernel, convolutional kernel, is concentrated near identity? What would this mean? I mean, for example, when you're doing regular convolution, let's say in 1D or 2D, your kernel can be any function that could be have a large distribution. But when we're dealing with, let's say, CNNs, convolutional neural networks, we pick the kernel size to be very small. What does that mean? It means that we're choosing this function, this kernel, this distribution over the group itself, over the translation group in that case, to be very concentrated, to be non-zero only around identity and 0 otherwise. So then we asked the same question here. We said, okay, what if your kernel in this group convolution is concentrated around identity with a small width? What is this going to become? So you can do a simple Taylor expansion of this f of gv term and see that the v term, which is what we're doing the integral over, if you do if you assume that this kappa is only non-zero when v is close to identity, you can write this v as identity plus epsilon L, like what we did for the when I was talking about the Lie algebra. So we're essentially writing this as identity plus epsilon L. And if you do that, then you can expand this f of gv. You can expand this up to first order in epsilon by writing this v as I plus epsilon. And then what you get is you will have all of the v terms basically come out of f of v. Basically, when you do this expansion, you're expanding around f of g. Maybe I should write this down. Basically, for this expansion, this becomes f of g plus epsilon times gl. So you have one term that is f of g, that is the point around which you are expanding, and then you're adding an epsilon gl to it, and that is where the second term comes in. So now, because the point that you're expanding around doesn't have the v in it anymore, it doesn't have the epsilon in it anymore, essentially f of g comes out of the integral, and all of the integration is summarized into this coefficient epsilon bar and this other coefficient w0, which comes from what the kernel was, what this kappa was. So what is this saying? This is basically saying that for kernels that are concentrated near identity, you don't need to do the integral. You don't need to do the sampling over the whole group, obviously, because you're only dealing with small group elements. And therefore, the whole sampling and discretization of the group is not necessary for these small kernels. Okay, and I see there's a question.
Yeah, so here when you say like it's close to the identity, you're talking about the width here. But suppose that you have a transformation that is just minus identity. Like basically you multiply the previous image by -1.
Oh,
and in that case, like can you actually write that it's a transformation with the epsilon term here?
so that's an interesting question, because the minus, that basically that reflection that you're talking about, that is not a continuous transformation. Essentially, you can show that you can never write that as an exponential map from this group element to basically from the original element to this new element, if you are dealing with rotations, for example. Let me put it this way. First of all, the group of rotations itself doesn't include reflections, the rotations in 2D, for example. It doesn't include the -1 multiplication. And for transformations that are discrete like that, there is a separate step that you need to define, that you can talk about the transformations that are continuous, and then the transformations that are discrete are essentially a separate transformation that I don't know how to write right now in terms of this kappa of V, but I know that we thought about it, and there is actually also in the appendix of this other paper that, let me bring this up again here. If you look at this paper, I have to look up the exact name, but Mark Finzi and I think Max Welling and some others have this paper from 2021. I think it's called like a practical method for implementing like symmetries and stuff like that. In the appendix of that one, it talks about those discrete transformations. When you're doing reflections, how do you deal with, how do you include such transformations also into the architecture? But your question was
yeah, because there are some kernels like that are not possible via this transformation. Like here, are you considering only using like, for example, I think you're working with 2D rotations. So are you considering only like using 2D rotations, but then you will miss out this kind of trivial transformation for a regular convolutional neural network? And you could miss, for example, some kind of transformation that we know are important, for example, the Laplacian operator, which also cannot be expressed in terms of convolution. So in terms of rotation invariance. So yeah, are you considering using a combination of these?
So the discrete transformations can easily be implemented by just having, because there are usually just a small number of them, for example, for these reflections or parity, and basically you can have reflections around each of the axes, for instance, in a rotation group. You can include them as, just encode them as the same way that people did for encoding discrete transformations into your neural network, which basically means that you have just one copy, one route that goes out, and instead of this group element, this identity plus GL being multiplied into it, it also has the reflection multiplied on the outside into it. So that would give you, when epsilon is 0, the reflection times identity times your original element is what you're looking for, right? So -1 times your original element. So those are actually simple to implement. But for Laplacian, I haven't thought about that. Maybe you should describe that to me better so that maybe I can see what you're talking about. You're talking about the graph Laplacian?
Well, not necessarily the graph Laplacian, but just you can think about the discrete Laplacian kernel, for example. If you have your small kernel of 3 by 3, where you have 4 in the center and -1 for all of the neighboring elements. So it's basically like how much there's a signal change in that area. What's the so this is the second derivative, basically.
Yeah.
And
so I have something at the end that might be related to this, because you can write this Laplacian using the incidence matrix of a graph as basically incidence times incidence transpose. And essentially, if you use a, so what I'm going to show for the implementation, and I don't want to hold you guys up for a long time. I feel I spent all the time on the slides actually, but what I'm going to show is that for the implementation for this derivative, you can basically, this becomes a set of partial derivatives, like is written here in the last line. And these partial derivatives, you can implement using discrete derivatives, basically, which you can implement as the what is called the incidence matrix of a graph, which is a graph that's capturing the topology, and then you're just doing a +1, -1 along every edge in that graph. And from that incidence matrix, you can also have Laplacians in the, for instance, if you write down a loss function for this layer, like a mean square error loss for a single layer of this neural network, it implicitly has the graph Laplacian, basically has the discrete Laplacian in it, because it has 2 first order terms. And if you do a partial integration, you get the discrete Laplacian basically acting on your feature map. So maybe that's one way that the Laplacian can appear in these terms. You can also talk about basically second order terms if you want to keep them, and maybe that would be another way that the Laplacian could appear. But I think, yeah, I think I could maybe learn more detail about what you mean. Yeah, maybe after discussion.
I think it makes sense. Thank you.
Sure. Yeah. And here, this was a very simple step. It was just showing that if you have a kernel localizer on identity, if you expand the integral, you don't need to do the integral. The integral is basically captured in these coefficients. So all you need to learn is basically these coefficients for these this Taylor expansion. So the number of these epsilons is the number of the Lie algebra bases that you have. So for instance, if you have the 2D rotation, you have just one L. So you have just one set of epsilons that you need to learn. You may increase their number to capture just more angles, but there's essentially one number per each L that for each transformation that you need to learn.
And you also need to learn the generalizes, right?
So if you want to, for example, if you don't want to hand code the symmetry into your network and want to learn what symmetry is in the data, then you can learn the L as well. Okay. Yes. But since you're not learning 1,000, let's say, 2x2 matrices, rather you're just learning one 2x2 matrix, it's easier to actually learn it this way. And the other important thing is, I mean, the step that really makes this useful is probably this step. So here, this was nothing special. This was just a Taylor expansion to first order of what people already had. Then here we just show that you can actually combine these layers. If you use a multi-layer version of this, every layer can help you move the kernel a little bit away from identity. So because technically every layer, what it's doing is it's doing a small group transformation, and basically this group transformation becomes then, if it's acting on an existing layer, then this becomes a transformation on the location of the kernel in the previous layer. So it just moves the kernel a little bit away from identity. Similarly, if you have a kernel that's far away from identity, you can write it as a multi-layer version of, these layers of the basic layer, so that that kernel that's far away from identity slowly moves towards identity and becomes the basic layer that we had in the previous state. Bottom line is combining multiple layers of this simple kernel that's focused around identity. What you can get is a bunch of kernels that are localized at different points on the group manifold. And by summing them up, you can basically construct any distribution on your group manifold, any kernel on your group manifold, which basically is what all the other group convolutional neural networks use.
Is there like a relation to the field of view, so to say, of a CNN and the number of layers?
Yeah, exactly. So when you as in the CNN, when you're increasing the number of layers and you can increase the field of view, the kernel size, basically the coverage of one kernel in the higher layer, it can basically cover a large area in the lower layer. It's exactly the same idea.
Okay.
So the same
in
way,
some sense.
What is it?
In some sense, in ResNet, for example, the kernels being small and the fact that we use patch norm and residual connection, it enforces the transformation of each layer to be a perturbation over the identity. And I think this is a similar idea, like you're saying that many layers of small perturbation over the identity can yield to some very important results.
Interesting. Yeah, I should look into that too. Yes, that's basically exactly what we're saying here. Basically, small layers that are doing small transformations close to the identity can be combined to create large transformations. And the point is, this is not completely replacing or in a revolutionary way, like getting rid of like the discretization. It's just saying that instead of you having to sample a large number of things from the beginning, instead, just let the network learn what it needs to sample from. What are the number of, how far does it need to go? How large does this kernel distribution in the end need to be? All of these are just learned by learning these epsilons that each of those layers is learning. And you can share the L's in all of these layers if you just want to make sure that this is, using the same Lie algebra. And you're just learning those parameters, and the Lie algebra basis is the shared part that you can keep throughout all of these layers. And so this is basically the main theorem that we had in the paper, which is basically saying that with these small, simple Lie algebra convolutional neural network layers, you can approximate any group convolutional neural network layer. And the other thing is, the other theorem in Condor and Trivedi was that if you have pointwise nonlinearities, they are also equivariant. And because our layer is just an expansion of the same equivariant layer that they had, their theorem, which was saying that any feed-forward neural network that is equivariant has to be implementing group convolution and some pointwise nonlinearity, that theorem just becomes, a corollary to our theorem becomes that every feed-forward equivariant neural network can be approximated using these, using a multi-layer L-Conv with like pointwise nonlinearities. Okay, so I know it's been a very long time, and maybe, I guess people might want to leave soon. So I'm just gonna quickly wrap up some things. So there are a lot of things about implementation that I could talk about. These are details that are not that important, but as I just briefly mentioned, you can implement those derivatives. So there was one thing that I skimmed through over here. So in this expansion, this is basically what is representing the layer. And here there's a complicated derivative over the group, but you can rewrite it as a derivative over the space. So this is technically a vector field over the parameter space. Oh, sorry, over the space of your coordinates, like your x. So these are a set of partial derivatives. And then you can, if you're dealing with discrete spaces, let's say you have a digital image, so it has like discrete number of pixels and stuff. Instead of doing these derivatives, you can have a set of linear transformations that you can implement with like, you know, the incidence matrix of the lattice of the pixels and stuff like that. But in the simplest form, you can think of that whole vector field, that whole derivative term, as just one big matrix that's acting on all of the pixels to all other pixels. And that is like essentially a big graph that you are implementing into your neural network. For each of your, so for each of your Li, for each of your Lie algebra elements, you have a structure like this, which is essentially just a, if you think of this as just one matrix acting on a feature vector f, so here all of your features have been vectorized, like you have flattened your image into one large vector. And what this is, what the action of our layer looks like in this case is just simply a graph convolutional neural network with a graph convolutional network with the LIs, these Lie algebra elements being the graph structures.
So
and so
we could, for example, like we don't treat our image now as an image, but we instead go ahead and treat it as a single vector and are then taking this huge matrix. Let's say we learn this huge matrix, or no, let's say we don't learn this huge matrix, then we need to parameterize it in a smart way where everything is zero except for a few spots, to then also get the translation symmetry that we would usually have when sliding our kernel over this. And now, if instead we say the L is learned, then we hope that the network itself figures out that maybe we have translation symmetry and we make everything zero in this weight matrix except for the few spots.
Exactly. So there's two strategies for when you're learning it, and this is a complicated slide. I'm not going to go over it, but I'm just saying there's a formula that you can follow for having a very sparse encoding of that matrix L, because as you said, this L can be a huge matrix if it's from all pixels to all pixels. But if we want the L's to be mostly non-zero for pixels that are close to each other, then you can think of that as a graph between the pixels. And you can take the incidence matrix of that graph that I'm representing as this B here, and write the L's, the components of this, each of these L matrices, so L mu nu, you can write its components using this graph structure and some small matrices that you need to learn. So this can make it much, much sparser than that huge matrix for learning. In practice, I haven't implemented this yet. Instead, I did the blind thing of like, so this is not that important, of trying to encode the whole big matrix. This is one example for what that L looks like for 2D rotations. There are actually a lot of long range connections because if you don't include these, so what I mean by long range connections here is that it's like a resonances that you get when you're doing like a discrete Fourier series. You might have these fluctuations happening far away. If you want to get an accurate description of a function using on a discrete space, you get these resonances like this. So this is what the Lie algebra element for a 2D rotation on an image that would do this kind of transformation looks like as a big matrix. And here, this was a small.
yeah, if this is now the ground truth L that we would like to discover if we were to learn it,
Exactly.
but is this unique? Like, could we, like, it also depends on the epsilons that we're learning, right? And could we have different epsilons combined with different L's to end up with the same result?
So technically you can. So for example, you can multiply the epsilon by 2, divide the L by 2,
Yeah.
so that the epsilon times L would stay the same. So yes, you do have that kind of degree of freedom, but if you put some constraint on L and say, I want its magnitude, for example, its norm to be 1 or something like that.
Okay.
There are actually norms that you can define in Lie algebras. I mean, one way to define them is this metric called the killing form. And it defines a metric that you can use to normalize your Lie algebra basis. In our test, we didn't use it, but you can do that. Basically, you can have extra regularizers to basically so that you have one standard form of L that you're finding. But in addition to that, there's more degrees of freedom, as you might think. Like, for example, when we talked about LXYZ for the rotations in 3D, your choice of what is XYZ is up to you. Therefore, any kind of rotations to your frame is also allowed. And if you don't enforce orthogonality between your generators, there is even more degrees of freedom. It's like, when we're learning feature maps, we usually don't force them to be orthogonal to each other. So you may have redundant features as well when you're learning, let's say, feature maps using a CNN. In a similar fashion, your L's might have linear dependence on each other, might not be completely linearly independent. And you might want some of those properties if you want, but if you want them, you need to add some regularizers to include them, because a priori, any of those solutions is valid. If you have a bunch of L's, as long as they, cover the whole space, all the directions, they don't have to be orthogonal vectors, they just have to form a basis for the space. So yes, you're right. There are a lot of degrees of freedom that might, obscure this. But in this case, because there's just one L, the only degree of freedom is really the magnitude of it, because there's only one dimension that it needs to learn. So we do expect to see something that's more canonical like this.
Okay.
And this is basically the result that we get with tests. Here at the bottom, I'm just comparing it with like what you would get if you would try to use like a small transformation and extract the L from it. From a really small transformation, you don't discover these long range dependencies. But what is the setup of this experiment that we did here? Basically, I designed this augmentation task here where I'm feeding like 2 types of random inputs, and they're like really tiny images, like 7 by 7 images. And one of them is rotated by some angle relative to the original one. And what I'm doing is I'm asking the system to predict the rotation angle. So in the end, I have like a 1-layer or 2-layer MLP that does the prediction. But before that, I feed one of the inputs into a recurrent L-Conv. L-Conv is our layer, basically Lie Algebra Convolutional layer. And what this recurrent layer is supposed to do is it's supposed to basically figure out by what angle this one is rotated, so that in the next step, when I take the dot product of this with this, it becomes something from which I can easily extract the angle. And this looks a little bit handcrafted, a little bit black boxy in a way, but I just wanted the task to be such that we could clearly say that if this system wants to be able to match these patterns well, it actually has to find the rotation, learn the rotations. And what happened here is after we trained this, I just opened this layer up and looked at the L term in the L-Conv. So this L here is that giant matrix that is supposed to look like this. And fortunately, in this case, it does have a lot of the similar structures. You also see some of these longer range connections. It's not perfect, obviously. It's not zero also all these places that we don't want it to have terms, that it should be close to zero. Again, this is because I did the brute force version, not the sparsified version where I use the incidence matrix or information about which pixel is close to which pixel. So I just did a brute force search, assuming all the pixels could go to all pixels. And here the result was fairly good. There was like 70% almost correlation with the ground truth. I did some, I just, go ahead.
If we now just had a feed-forward neural network, like that takes the whole image as input, fully connected, takes gives the whole vector as output, the weight matrix would look nothing like that, right? If to us, it would just look like noise.
I think so, yes, in most cases. And I think like you need actually a pretty wide layer here in the middle to be able to do this, because it has to capture all these different, it's taking two versions of this image as input and it's trying to map them to each other. So first of all, it has a lot more parameters. And secondly, it probably looks like noise. I should actually show those other tests alongside of it and to see like how they compare.
But I mean, then this is just pretty awesome.
Yeah, so this is the good news. So yes, this was exciting, and this is to see that yes, you could at least in principle discover one of the L's. But I should also point out that this kind of brute force method and direct way of measuring this is not a great way. Actually, in the paper, in the appendix, I have an example, I think another example of this for like a larger image, and it's just doing very bad. Like it's not, oops, is the SI not here? Oh, sorry, this version doesn't have the SI. Okay, I'll open the SI version. Let me see, is this,
I mean,
I think this should do it.
no, yeah.
Okay, good. So yeah, these were some other tests that I was excited about, but yeah. So I think this is one other version. I think this is for a 20 by 20 image, I think, if I remember correctly. Here you still see a lot of the interesting structure, but it has much less correlation with the ground truth. So this is still pretty exciting in terms of what it can do, but it's not as good as I wanted it to be, and it's not perfect. It feels more like the L it has some higher order resonances. I think it's not just L to the first order. It might be L to second order, third order, maybe because that was helping with learning the angle. So I should say two things here. This is with a larger range for angles of rotation, as well as a larger image where the correlation dropped rapidly.
I still think it looks very good. Like personally, I think perhaps the metric of correlation is not the best metric to measure how much the pattern match. Yeah, I think the pattern do match a lot from what I'm seeing.
Okay, yeah, so that's also a good point. I'm still though thinking about different ways that we could make this smarter. I think maybe doing something like meta learning the L's in a separate step and learning the thetas in another step could maybe improve things. I don't know. I would definitely love to do more tests or see some people doing tests and saying what works and what doesn't. And especially also, I didn't have the time to do the like more complicated groups. I would love to do like an actual like SO3, for example, where you actually have like 3 matrices and then use the sparse structure, have some regularizers for enforcing orthogonality between your Lie algebra basis, those are some of the things that I wanted to do that I didn't get to do at this stage. Maybe I'll do it for the follow-up paper now that I'm settled, hopefully. Yeah. And I think one other thing that I wanted to say about that, maybe the last thing. Oh, actually, yeah, okay. So let me skip that. So let me just maybe wrap up because I think everybody maybe wants to leave or something. Obviously, I'm very excited about that part, and I do want things to improve. I want people to figure out problems with how we're doing it and see if there are better ways to do it and improve that. I just wanted to say one last thing about what I'm excited about here about this paper. So again, I don't know if there are any physicists in the audience, but the one of the last things we discovered in the paper was that if you so physicists have been trying to learn or have models that encode symmetries and that could be used for describing systems before. So I basically asked the question, okay, what is the relationship between what we're doing here with symmetry equivariant neural networks and what physicists have been doing for years? And I knew that physicists, you're usually looking at dynamics and usually looking at infinitesimal steps in time and so on. So I knew that maybe, with what we're doing here with infinitesimal transformation, there might be a relationship. Physicists usually start from an objective function called, let's say, Lagrangian, or its integral, which is the action. And then they do an optimization on that to get the equations of motion, the physics of the dynamics. And I said, okay, so in machine learning.
Can we maybe go to an example level on that? Like,
yeah,
so Lagrangian could be.
So, for example, for Newtonian physics, if you want to find the Newton's equation of motion, which is F equals ma, so the force is equal to mass times acceleration, and the force can be, for example, expressed as the gradient of a potential energy. So Newton's equation becomes mass times acceleration, which is second derivative of positions with respect to time. So mx double dot, that plus gradient of a potential energy equals 0. So that is basically Newton's equation.
Okay, but what is the Lagrangian for that?
Yes, so the Lagrangian is a function that if you do basically a maximization on that or minimization on that, you get the equation of motion. The Lagrangian that will give you Newton's equation is actually kinetic energy minus potential energy integrated over time. So if you write down the kinetic energy, which is mv squared, so mx dot squared over 2 minus potential energy, and you integrate that over time. If you now say, give me the x as a function of t, which extremizes this objective function, you get Newton's equations of motion.
Okay, so you go ahead, take potential energy minus kinetic energy, you call that the Lagrangian, and then you go ahead and integrate that over time. That's what you call the action, and that's what you minimize. And if you minimize it, you end up finding out we need F to be equal to ma for this thing to be as small as possible.
Exactly. So that F equals ma, you can derive it as the basically the solution x of t that is extremizing that Lagrangian or that action. So physicists start from there and basically get their starting point. One way to do physics is to find out how to write down that Lagrangian. What would be the Lagrangian that when you extremize it, its extrema define the behavior of the physical motions of particles or states and things like that. And in machine learning, we're doing something similar. We have a loss function. We try to minimize the loss function, and the minima of the loss function are supposed to show us the more likely states. Technically, from a quantum point of view, that's also what the action should do. Instead of saying the extrema show the exact solutions, you say the lower action states have higher likelihood of occurring in nature. So I basically said, okay, what if we take the architecture that we just built, write down the simplest simplest loss function that you can for it, and see what it looks like compared with physics. And lo and behold, if you take a single layer L-Conv, the neural networks that we introduced, do a mean square error loss for that single layer in the simplest setting where you have just one input and no output. Basically, this phi is both your input and output. Then the mean square error looks exactly like the simplest kind of Lagrangian that people write in physics for continuous spaces. It's called the free field theory Lagrangian. Technically, that F equals MA case that I just talked about is also a special case of this. If your space is one-dimensional and it's only time, so if x, this dn of x, which is your space-time that you're integrating over, is only time, so it's just dt, and your phi's are your x of t, your positions of your particles with respect to time. Basically, this second term that you see here becomes dt of x and dt of x. Basically, this becomes the kinetic energy. And this other term is a potential energy, which is technically a harmonic oscillator potential energy. And this is a term that becomes zero when you integrate, do the partial integration. So essentially, the simplest case of L-Conv gives you the simplest Lagrangian in physics. So one thing that I'm excited about is to see, okay, what if you do some architectural design, and what if you have like a multi-layer L-Conv or like some more sophisticated architecture? What physics model does it is it equivalent to, and what can it be used for in physics? Okay, sorry for taking so much over time and staying so much over time, and I
think it's entirely inappropriate for apologizing for giving us a lot of amazing information and for spending your time with us here. I mean, I think I'm very sure a lot of us highly appreciate it. At least for me, the paper is a lot clearer now, and the whole subject is a lot clearer now. Yeah.
Thank you. I hope so, because I guess it's a complicated paper. So
I really enjoyed this discussion. I hope you also did. Dom, you wanted to say something?
I just want to say that it was a very good presentation, and I think like very informative for everyone. The fact that there's still so many people attending, despite like being on different time zone and having different schedules, I think it shows like a lot about the quality of the paper and the work that you presented today. And thank you also for jumping in and helping people who are not really familiar with Lie algebra to really understand the group theory and Lie algebra enough for your paper.
Thank you.
Lie algebra.
Okay. No, thank you. Thank you for having me. I didn't get to really read through the questions, but please feel free to email me, if you have more questions or if you want to discuss anything more. I'd be happy to discuss these. And I'll be starting to work on a follow-up paper actually now that I'm settled back. So
okay, so only starting. No, we can't have our hopes high that the next NeurIPS has the follow-up paper. So let's look forward to that NeurIPS follow-up. Hopefully Professor Dehmamy makes it. And but this one was definitely already very awesome, and I hope we can discover more symmetries in the future with better methods like that. And if you want to join the reading group sessions yourself, the information is in the description. Also, we have a Slack channel or a mailing list where you can sign up for weekly reminders about the papers that we'll cover next.